things have to last for 30 years when you put them in the ground or put them under the ocean, right? So this is emphatically permanent, okay? All right, so this is a typical spectrum, okay? And we're going to operate on the low wavelength side, the short wavelength side, and the reason is that there the dispersion is enormous, and we see these solitons effects. I should have mentioned it, okay? And we choose 4 different frequencies where the linear rejection rate varies between -25 and -40 dB, and now we're going to crank up the intensity and see what happens. And for the -40 dB results, you see that if you increase your peak power to about 1.5 kilowatts or so, the intensity the transmitted intensity goes up and then saturates at about -6 or -7 dB. That's essentially full transmission. But nonlinear experiments are difficult. Okay, but so this is the same as that for the purposes of this presentation. And you can do this with the other frequencies as well, and they all of course have the same behavior, which is what you might expect, of course. Let's now look at just this trace in particular, and look at the transmission now as a function of time. Let's time resolve it. And I should say, yes, at these high intensities, everything comes through because it tunes itself outside the band. Okay, so at the highest intensity we put the light in, you get a pulse out, and it is delayed from your input pulse by 1.6 or so nanoseconds. The fractional delay is significant compared to the pulse width, and the pulse, in spite of this very, very strong dispersion, in fact, not only has it not broadened, it has actually become narrow because of these soliton effects that I was mentioning earlier. You can now vary your incident power. And I should say this red curve here is the pulse that you would get out if the light just flushed through its ceiling. Okay? And so at these higher powers, the simulations are very easy. There's standard routines for that. And you can see that apart from offset, the two are in reasonable agreement. In fact, in the experiments, the powers are slightly lower than we expect. Usually when you do experiments, things work out worse. In this case, we get a better deal out of it. Okay? And this was a more recent result that we obtained with a longer grating, and we have longer delays, 3.2 nanoseconds. Okay, so this is the nonlinear slow light. Let me just finish this section here, right? So in spite of the fact that you have massive dispersion, there's no broadening because of this soliton effect by which the dispersion is balanced by the nonlinearity. Now, I just have 2 quick movies here to show you what happens. One of the things we can't do is look inside the grating and see what happens. So let me just very briefly and I don't know how to couple them to my presentation. I'm a bit of a Luddite, so. But this is happening in the linear regime, right? You come inside the band gap, the pulse comes in, and basically it gets reflected. You get this high peak because the incident and reflected pulse interfere with each other. At high intensities, you get this slowly propagating pulse with higher intensity than your output pulse because of the slowness. And let me just run it once more. But it kind of penetrates this fiber, propagates slowly. Once it makes it to the other end, it gets out, intensity goes down, a little bit reflects, and stays behind, integrating. Okay. Let us now go to high intensities. And 5. Man. Sorry, guys. Little teaching. Here. So now we go to higher intensities. And here I will get to explanation of this particular graph that I showed you earlier. And this is associated with the solitons, but there's another property of them that we will need for this. I discussed this one earlier, so let's move on. Well, the first thing you want to do when you find an experiment like that is see if it agrees with theory or simulation, to see if what you see is reasonable or not. Now, at low intensities, well, this is what you find. In theory, of course, it starts at 0 and goes to 1. In experiments, as I discussed earlier, it doesn't. High intensities, you get these steps. And in your simulations, you get these steps as well. So this is a fixed input intensity. You vary the frequency. And you get this step-like behavior, just like it is here. And if you go to even higher intensities, you get even more distinct steps. Now, what is happening there? Well, I'm afraid that I will have to show you a few more movies, and I'll have to go outside the system again. But hopefully this time I can come back to the same slide. This is the first step. This is my grating here schematically. This is my incident pulse. I'm now at this high intensity. And this is very similar to what I showed before, right? You have this slowly propagating pulse, and once it leaves the grating, it's out of there very fast, low, with a lower intensity, because it travels faster. Let's now go to the third step, the other dot that I have there. There are 3 solitons, right? So, apparently each of those steps corresponds to one more soliton coming through there. Now, then there's a number of questions. Okay, so this gives us a hint of what is happening. The steps are somehow, by ways that we haven't really discussed yet, and I will do in the next little while.